All right, today we're going to dive into the hidden world of chemistry that, believe it or not, completely shapes our sense of smell. We're going to explore the molecules behind some of the most powerful scents we experience every day, from the sweetest smells to the sharpest stings.
So let's start with a little puzzle. What on earth could possibly connect the smell of a ripe banana, the sharp tang of vinegar, and that chemical punch of nail polish remover? I mean, they seem totally, completely different, right? Well, it turns out they all share a secret chemical connection.
And no, it's not just a coincidence. The link is one surprisingly simple, but incredibly powerful piece of molecular design. It's a fundamental structure that nature uses to build a massive library of different substances. And that key player, the hero of our story today, is the carbonyl group. This is the fundamental building block we're going to be talking about. It's what ties all those different smells together, and so much more.
So what is it exactly? A carbonyl group is actually beautiful in its simplicity. It's just one carbon atom sharing a double bond with one oxygen atom. That's it. This COO structure is at the very heart of every single molecule we're going to look at. And this is where the magic really happens. The best way to think about the carbonyl group is like a central Lego brick. By itself, it's just one simple piece. But depending on what other bricks you snap onto it, you can build completely different molecules with wildly different personalities. Okay, so let's start building. Our first family of compounds built from this carbonyl brick are the aldehydes and the ketones. These two are some of the simplest and most common variations you'll find. You know, the difference between these two is surprisingly small, but it changes everything. With an aldehyde, the main carbonyl carbon is bonded to at least one hydrogen atom. But with a ketone, that same carbon is sandwiched right between two other carbon atoms. It's a tiny distinction on paper, but it's absolutely crucial. A classic example of an aldehyde, though maybe a pungent one, is formaldehyde. You might know its sharp, really irritating smell. Its ability to basically set proteins, causing them to coagulate, is what makes it such an amazing preservative for biological specimens. And it's also a key ingredient for making super durable plastics like Bakelite. Now for the ketones. A very familiar one is acetone. Yep, that's the unmistakable smell in nail polish remover. As the simplest ketone, it's an incredible solvent. It can dissolve all sorts of things, from varnishes to certain plastics, which makes it a real industrial workhorse for manufacturing all kinds of goods. Okay, so what happens when we snap another piece onto our carbonyl brick? What if we add a little more complexity? Well, that brings us to our next major family, carboxylic acids and esters. So the critical difference here is the addition of a second oxygen atom. In a carboxylic acid, the carbonyl carbon is attached directly to what we call a hydroxyl, or an OH group. But in an ester, that second oxygen acts like a little bridge, connecting the carbonyl to a whole other carbon group. Again, a tiny structural tweak that creates a whole world of difference. Remember the smell of vinegar from our opening question? Well, you can thank acetic acid for that. It's a classic carboxylic acid, and it's the active ingredient that gives vinegar its signature sour taste and sharp, tangy odor. And here's a fantastic bit of chemical trivia for you. The simplest carboxylic acid is called formic acid, and its name comes from the Latin word formicus, which means ant. Why? Because it was first isolated by, you guessed it, distilling red ants. It's actually the stuff that gives ant bites their sting. All right, now for esters. If carboxylic acids are often sharp and pungent, esters, well, they're the artists of the chemical world. These are the molecules responsible for the huge variety of sweet, fruity, and just plain pleasant smells we find in nature. And because they're often small and volatile, they can float right up into the air and into our noses, creating the aromas of everything from flowers to, yes, ripe bananas. And get this, the complex, amazing flavor of a single strawberry isn't from just one or two molecules. Scientists have identified over 350 different volatile compounds in there, and a huge chunk of them are esters. That's the incredible chemical symphony packed into just one bite of fruit. So, we've met the different families, but how are they even made? Let's take a quick peek at the process, because it really shows why this chemistry is so fundamental. This isn't just about smells, you see. Carbonyls are essential building blocks in everything from biology to medicine. The core process is a reaction called oxidation. But in simple terms, think of it like a recipe. You start with an alcohol. Then, through oxidation, you swap out a carbon-hydrogen bond for a new carbon-oxygen bond. And just like that, boom, you've formed a carbonyl compound. And that is the key takeaway here. This one fundamental process, oxidation, is like a gateway. It's how nature and chemists can transform simpler alcohols into this huge, diverse world of carbonyls. It unlocks an incredible range of smells, tastes, and functions that are vital for, well, pretty much everything.
So let's wrap up with a quick field guide. When you smell pungent preservatives, think aldehydes. For powerful solvents like nail polish remover, that's a ketone. That sharp, tangy smell of vinegar, you're smelling a carboxylic acid. And for all those wonderful, sweet smells of fruits and flowers, you've got esters to thank. And every single one of them is built from that simple, elegant C double bond O.
From preserving life in a lab to creating the beautiful sense of a garden, the chemistry of the carbonyl group is truly all around us. So now that you know what to look for, it kind of makes you wonder, right? What other parts of your world are being shaped by this amazing, unseen chemistry?